All the formulas we originally memorized are represented in this graph. By drawing the graph, you can solve all the problems, and sometimes we'll also try deriving formulas using the graph. Hello and welcome, I'm Minsikham from Minsikham Academy. Let's commit to an hour of physics a day. Today we're going to cover the three key elements of motion. But first we'll start with a brief look at the difference between Newtonian mechanics, also called classical mechanics, and quantum mechanics, the foundation of modern physics. To begin, for our engineering students, the four major mechanics you will be learning are all fundamentally based on Newtonian mechanics. This means we solve problems using the principles of Newton's mechanics. These four major mechanics are dynamics, solid mechanics, fluid mechanics, and thermodynamics. On the other hand, students in the natural sciences, specifically physics majors, do learn classical mechanics, but they tend to focus more on modern physics, like quantum mechanics. And in the case of general physics, it's general, right? You learn everything in a broad range. You learn some modern physics and some classical mechanics. Got it? It's all included. Let's first look at the features. First, in Newtonian mechanics, the scale is large. This means it's large enough to be seen. In English, it's called macro scale. On the other hand, quantum mechanics deals with the small scale. It is micro scale. Now, not just the size, but there's a difference in speed as well. But this is all relative. Compared to quantum mechanics, we'll just call its velocity v. This v is extremely slow, at least compared to quantum mechanics, right? In quantum mechanics, however, the velocities are extremely high. These two characteristics lead to a key principle of Newtonian mechanics: certainty. Because we're dealing with visible objects at relatively low speeds, we can know exactly where an object is. This is why Newtonian mechanics is used for predicting the future. In quantum mechanics, however, things are so fast and invisible that they can only be described probabilistically. That's why the uncertainty principle is the core concept. An object might be in a certain place, or it might not. It's moving so fast that you simply can't be certain of its exact position, whether it's here or over there. So, while these two fields are different, our focus will be on the concepts of certainty and future prediction. As we go on to learn not only motion but also other topics in general physics, like thermodynamics and fluid mechanics. So remember that they are all based on future prediction and certainty, and it will make studying physics a bit more fun. This will make it a bit easier to understand. So let's take an example. Let's say we have a rocket here. A rocket. I'm going to illustrate this difference with a graph. Let's say we apply a constant acceleration to this rocket. In other words, we're continuously feeding it fuel without interruption. So if acceleration is constant over time, what happens to the velocity? It increases, of course. So the velocity keeps increasing linearly like this. However, the limitation of Newtonian mechanics is that while it works well at low speeds, it breaks down as we approach the speed of light, c, which is 3 times 10 to the power of 8 meters per second. Eventually, the object's velocity would surpass the speed of light. This implies that you can actually overtake the speed of light. This is the prediction according to Newtonian mechanics, right? The logic is if you can just keep adding energy, you'll eventually move faster than light. This is the Newtonian perspective. And while this perspective holds true for low velocity, it becomes incorrect as the velocity increases. This is where Einstein's theory of relativity comes in. It was this theory that proved the Newtonian view was wrong. According to the theory of relativity, an object's velocity, v, can never be faster than light. Because of this premise, if we set the speed of light, c, as a limit, the theory of relativity initially aligns with Newtonian mechanics, but the graph starts to curve as velocity increases. Eventually, the acceleration must converge to zero. And that's why nothing can surpass the speed of light. We'll cover this topic in more detail later in the course when we get to the theory of relativity. All right? For now, just remember that we're studying Newtonian mechanics for the purpose of future prediction. All right? Because the topic we're starting with today is motion itself. All right, then let's look at the next page. Now, the three elements of motion. To understand an object, there are physical quantities desired in physics. When an object moves like this, we say it is in motion. Then there will be acceleration, there will be speed on the graph, and there will be distance like this. Physics doesn't ask, what color is the object? It just doesn't. Color, there is no interest in color, none at all. Or, what are its hobbies? It simply doesn't care. So what does physics want to know? What is the object's state of motion? Just this. State of motion. It's the only thing physics cares about, and the only thing on your exams. The key values for this state are the three elements of motion. All right, let's take a look here. The first element is acceleration. It's represented by the symbol A, just like this, A. Next up is velocity, which we denote with the symbol V. Next is displacement, usually represented by an S. Some textbooks also use an X. The S likely comes from the work formula, W equals Fs. Though, to be honest, I'm not sure what it stands for, right? And sometimes it's written as D for distance. So the symbol can be D or S or X. All right? I'm more used to S, so I'll be calling it an ST graph. So, state of motion refers to A, V, and S. Exams will ask for these three, for example, at time t equals 0, at time 0. What's its acceleration? What's its velocity? And what's its position? They ask questions like that. Or, how long to reach a certain position? They can also ask it in reverse. Makes sense. Find the time at t prime. What is that time? If velocity is x, what's a? They only ask about these three things. Know these three and you've solved the problem. So I'm going to solve every problem with graphs. We'll master everything by drawing them. All right? So this method lets us know the object's current and future states. For example, if the current state is this blue dot, we can predict its future state too. Make sense? It's future. So what's a good real-world example of Newtonian future prediction for students? The GPS navigation in your car. It's probably the most common one you experience. Think about a GPS route, Seoul to Busan. First, you see the distance, right? About 440 kilometers. And what else do you see? An estimated time, your ETA. It tells you something like 5 hours and 10 minutes. This ETA is calculated using Newtonian mechanics. For example, of 440 kilometers, 400 kilometers might be highway, and 40 kilometers local roads. Driving 400 kilometers at 100 kilometers per hour would take about 4 hours, right? Or it might give a range, like 4 hours to 4 hours 20 minutes. This accounts for varying highway speeds of 90 to 100 kilometers per hour. Add about 1 hour 10 minutes for local roads, and you get a total of 5 hours 10 minutes. Of course, your GPS isn't perfectly accurate. It's not right to the minute or second, but it gets pretty close, right? Newtonian mechanics is the same way. Its key purpose is making rough predictions, in essence, predicting the future. So if you can draw these graphs, you can predict the future, right? If we can draw the AT, VT, and ST graphs, we'll know both the current and future states of motion. You'll be able to know all of this. All right? So just follow the method I use, and physics will become fun and easy. All right? Finally, for those asking, why use graphs and not formulas? Zrenia, I'll explain how a graph can represent all of those formulas. Many of you probably memorize formulas when studying motion. You memorize basic formulas, derived ones, converted ones. Well, you can forget all that. We're going to solve everything with graphs, but you need to know how the graph contains every formula. I'll derive one for you right now to show you. On graphs, constant acceleration is the most common exam problem. Let's call this acceleration a zero, and assume an initial velocity. With an initial velocity, the graph looks like this. And with an initial position, we get these graphs. They are a constant, a linear, and a quadratic function. This last one becomes a quadratic curve, like this. Okay, let's derive the formulas from the graph. This is to show the formulas are in the graph. First, the AT graph is a constant, a zero, right? A constant value, a zero. Next, we integrate this graph. We'll do an integration. I'll explain how to draw the graphs next time, all right? Today, we're just focusing on the derivation. The area in this AT graph is the change in velocity. Change in velocity. That's delta V, the change in velocity. Now, to derive the general VT graph formula, we just have to integrate this. We just need to do an indefinite integral. If we integrate a zero over time, we get a 0t plus c. Integrating with respect to time adds a constant. While c is just a constant in math, in physics it's the initial velocity, v0. That's v0. Next, the area under the VT graph is the displacement, s. More precisely, the change in position, delta s. So, how do we get the ST graph? We just need to find this area, and how do we find this area? Let's call this point time t, just t. So this length is t. And the area we're looking for is this section here, right here. This height here is delta v, and this is v0 initial velocity. So at time t, the velocity is v0 plus a0 times t. Now for the area of this blue trapezoid, the top base is v0 and the bottom base is here. This value, v0 plus a 0 times t. Now let's plug these values into the trapezoid area formula. The height here is t. To this area we add the initial position, s0. This acts as our integration constant. So c is simply our initial position, s0. If we expand this all out, what do we get? That famous formula you all know. You get the 1/2 ADD squared term and the v0 asterisk t term. The formulas you memorized are all in this graph, right here in the graph. So just draw the graph and you can solve any problem. Next time we'll practice drawing them to derive the formulas. So make sure you master this method. The next video is probably the most important. I'll show you how to solve any problem, so please focus. Let's keep studying hard. Great work today, and see you next time.